Hello everyone, welcome to an algebra tutorial video learning about exponential word problems and using exponential functions to solve these word problems. In this particular one, we're going to go over half-life and word problems that involve half-lives of substances. So it's a common one when you get into exponential decay. Either it's a half-life of a radioactive substance, or it's a half-life of a medicine, or there's just instances in life where certain things decay and we measure by how much those things decay or lose value in terms of its half-life. How long does it take before only half of it is left? So let's take a look at this problem here. We've got Motrin, or also called ibuprofen, is a common over-the-counter drug for pain relief. It has a half-life in the body of approximately 1.9 hours. If you take 400 milligrams of Motrin, how much will be left in your body after 10 hours? Okay, so the idea is you're taking medicine. It works for a while, right? And then eventually your headache comes back or your pain comes back. And if you read the directions on the back of the bottle, it'll tell you how often you can take it. Well, all of that is calculated both through biology and chemistry, but using math to figure out, based on how long it lasts in your body, how long does it take before you can safely take another dose. So this just says every 1.9 hours, only half of it is left in your body. So let's think about that a little bit. Let's make a little table here. So if I do hours and milligrams, after 0 hours, that's right when I take the pill, there's 400 milligrams in my body. After 1.9 hours, well, now there's only 200 milligrams left working in there. Another 1.9 hours, it's going to be 3.8 hours, so adding 1.9 again, now only half. Again, another half of that will be 100 milligrams. If I go another 1.9 hours, now I've reached a total of 5.7 hours. Well, now it'll be half again. There's only 50 milligrams left. And you can see why for ibuprofen, they say you can take another dose after 6 hours because, you know, compared to 400 to 50, that's almost all the way gone. And by the time you take another one and it starts working, that 50 might even be cut down to 20, 25 or so. It decays its rate, it's gone. But what we want to do now is write an exponential function that'll let us calculate, okay, based on any hours, not just these nice convenient ones, but after 10 hours, can we calculate exactly how many milligrams are left in our body? So let's talk a little more about half-life and how to use an exponential function. So half-life, you can use, there's a lot of different types of formulas. I'm going to use this one right here. The amount of a substance left after an initial amount, that's A sub 0, that just means a starting value, but it decays, it loses half of its value, so we got a half-life, so I'm going to multiply it by 1/2. And we're going to take it to the n divided by k power. All right, let's talk about what all these things mean here. A sub 0, that's just the beginning amount or initial amount of a substance, initial amount of something, right? Whether it's carbon-14 for carbon-14 dating, whether it's some other radioactive substance, whether it's some sort of medicine, anything, you have to start with an amount and then you start taking half of it from there. A is just the amount left, the amount remaining after all our half-lives are done. Remaining. N is the number of time periods So in this case, is it days? Is it hours? Is it months? Is it minutes? And K is the half-life of whatever substance we're doing. Okay, so let's use that to then write a function that we can use to represent this problem and solve it out. So in my function, I know my initial amount, we're starting with 400 milligrams. That's how much of the Motrin that we took at the very beginning. We know the number of time periods is going to be 10 hours. We don't know the amount remaining, that's what we're going to try and find, but we do know the half-life is 1.9 hours. Every 1.9 hours we lose half of that Motrin. 1.9, I got to use my units here, 1.9 hours. Okay, let's write a function now. So the amount left is equal to 400, that's my starting amount, I'm just putting that in place of a sub 0, times 1/2. We're going to do for 10 hours, but we're going to divide that by 1.9 hours because we're basically saying, okay, every 1.9 hours I lose half of it, so how many halves do I have to take? So 10 total hours divided by 1.9 tells me how many periods of 1/2 I'm going to have. All right, let's calculate all that out. Let's see what all that equals. Pull up my calculator here. 10 divided by 1.9 is equal to, change colors, so it turns into 400 times 1/2 to the 5.26, we'll round it to 3, 5.263 power. So that's about how many periods or how many times I want to take half of that substance. And if I just calculate all that out, 400 times 1/2 to the 5.263 power, I'm going to get 10, change it to 10.417, we'll round it to the nearest thousandth, 10.417 milligrams. There we go. If I start with 400, 10 hours later, I only have 10, just a little above 10 milligrams. That's not very much left, right? So that makes sense. 10 hours, if you can take a new drug dose for ibuprofen after 6 hours, then after 10 hours, you shouldn't have hardly any of the original amount left. There we go. We just answered our problem. Just to make things a little more interesting, I want to bring up a graph and a table so we can kind of see hour by hour in terms of what this exponential decay looks like here. Here is our graph. So you can see here's the function that I made. F of x equals 400 times 1/2 the half-life. There's my dividing by 1.9. That's the half-life there. And now you can see as I go hour by hour, there's all the way from 0 to 10 hours. We can see that we start with 400, 277, 192. It decreases until we get to the value we calculated. After about 10 hours, there's about 10.417 milligrams left. But we can see hour by hour, again, after only 1 hour, I still have a lot left. And in fact, up to 6 hours, I still have a pretty significant amount left. And we can see the nice exponential curve over here, an exponential decay. And it's slowly going out to 0 and flatlining out. And again, it's a good way to check your work. Make a graph, make a table, make sure your values are fitting with what you calculated. And it's a good way to make sense of everything that we've been doing up in the series with exponential curves, exponential functions, tables, and graphs. And now we're being able to apply it and understand, in this case, just the context of medicine and being able to take something in your body and knowing how long it'll last. Hopefully this was a helpful example for you to think about half-lives, how to calculate half-lives, and use exponential functions to model things decaying with a half-life rate.